Thanks.
Cool. All right, so I'm going to talk about functional reactive programming today. My name's Meiklejohn. That's my Twitter handle, so you should harass me because I really love that kind of stuff. I work at Bachelor Technologies. I'm a JavaScript and Erlang developer there. I also am a grad student at Brown University, where I'm doing some CS-related things there as well. Cool, so I kind of had trouble gauging the audience for this talk, so maybe we can just do like a show of hands. How many people have used functional reactive programming? All right, good. I hopefully that means I aimed it at the right crowd, because it seems like there are a lot fewer people who have actually used it. Okay, so we'll kind of just briefly talk about the motivations for doing functional reactive programming in JavaScript specifically, and these motivations are going to come like kind of straight from the Flapjacks paper, which also came out of Brown University, which predates me quite a bit, so I was not involved in that. So there's this notion of like void callbacks, or callbacks that basically map some type to void. In a lot of cases, forces mutation. So in this example here, we have basically a click handler that'll get some event, and if we wanted this function to be completely pure and return a value to something that was calling it and act on it, we can't really do that. So if we wanted to return like a computed value, not really. We kind of need to force like mutation of some sort of global state or some sort of state that it's been closed over. So there's one big motivation to kind of eliminate that, write as much of our code as pure code as possible, and be able to reason about our code a little bit easier and how it's going to execute. And then basically the second main motivation is going to be that you're going to have multiple places where variables are going to be assigned. And that makes it hard to kind of keep everything together. You can do a little bit of work to shuffle that around, but you still have assignment of variables that are shared amongst many functions that are happening, and the mutations happening at multiple places in your code. So in this example, we have a click handler for a particular event that's going to get some event, do some computation, and change some color of something on the page. And we also have this handle mouse over event. And let's say these are both going to change the background color. So the DOM is essentially mutable state. So this is mutation of the same thing happening in two places. And depending on how that should be set, that can become problematic. And, obviously obviously we can do a little bit of abstraction and indirection to make this like a little bit cleaner, but we're not really expressing the dependencies the way that we want to express them. So reactive programming is kind of going to reactive, and we'll talk about the differences between functional reactive and reactive programming. This is kind of a methodology for like addressing these things and writing easier to reason about code. So what is reactive programming? So in like a traditional kind of imperative program, you would have something like this. So if you imagine this is JavaScript, we have A being assigned to the values of B and C. A gets set, A is now set to that value. If B and C change, A doesn't change. And if A changes later, that's independent of B and C changing. So you're not really you're expressing a relationship at one point in the execution of a program, and not necessarily expressing a relationship of how these things should relate over time. And similarly, you're going to have this concept, same thing, just extrapolated. If C is now dependent on D and E, that slide is completely wrong, because that that really should be D is dependent on C and B, or B or any of the others. So let's skip over that because I screwed that up. So in reactive programming, what we essentially do is say A is related to B and C, and if B and C change, A should be recomputed. So we're essentially building a dependency tree here to say that the value of A is going to be dependent on the values of B and C, and then with this addition function applied to those values. So reactive programming has a lot of history in data flow languages. Obviously, we have like things like Verilog for hardware, and Lucid, and Lustre, I guess is how that might be pronounced. I don't actually know the pronunciation of it. So with that particular language, there's this kind of compelling paper about verifying critical systems by means of synchronous data flow languages. And this isn't directly related to FRP, but this paper demonstrates a really cool idea where they have a subway system, and they have variables that represent the presence of a train on a track. And then they want to control pathways through the subway system. And by what they want to do is express relationships to say that a particular thing is considered okay to go on to based on two other things. So if you have two tracks and then you have some sort of like connector between the two tracks, or some track that's going to move, you can say that this operation is okay to be performed if these certain preconditions are true. So it's an extremely declarative way to express dependencies in your program. And it also allows for some sort of static analysis on top of it to determine that certain conditions will never, ever happen based on these relationships that you express. So kind of what is functional reactive programming then? So functional reactive programming is going to be that kind of reactive programming model applied using functional programming techniques. So the concept of using operations like map and lift, if you're familiar with Haskell, and things like filtering events and delaying events and things like that. So we're going to see a ton of examples of this, so I'm not going to kind of dig into those just yet. So there are two main kind of data types in functional reactive programming. We have event streams, which are sometimes called just events or streams. We'll have behaviors, which we'll talk about in a second, which represents the different one. So event streams are, if you imagine an axis of time, event streams are, and you imagine this as a sequence of events, like an array or something like that, you have discrete occurrences over time of certain events happening. So you can imagine that like clicking on the mouse represent discrete occurrences of a particular event over like an axis of time. Another one is if you have a text field. The value of the text field wouldn't be this because the value of the text field has a value on continuous time. But change events to the text field, whether a key is pressed in that text field, that has discrete occurrences over time. So to give an example of event streams, we have like an idea of, and these event streams are composable, as we'll see. We have this idea of key presses. So we're monitoring key presses in a document, let's say. And then we only want key presses of the enter key. So we can compose this by applying a filter operation like you'd normally use in like functional programming or in many imperative programming languages have it as well. So we basically run this filter operation. The filter operation would be a function that would like kind of filter out key presses with like key code 32 or something. And then we basically get a new event stream emitted, which will be just key presses of the enter key. We also can branch off of that key press again and do another filter operation to get key presses of the space button. So these filter functions just will take any arbitrary code that's going to execute with the values as those values come into the stream. And then we also can do things like map. So we could say every time the key is pressed, we could just return 1 or 42 or whatever. So we're returning another discrete event stream that's being derived from the key presses stream but has a completely different value. So we're doing just a basic data transformation over that value. And we can also combine these event streams. So we have mouse events, let's just say it's every time the mouse moves, not the position of the mouse, but move events. And then we have key press events, and we can merge those into a stream. So it's important to realize that this mouse key, the MK circle there, will be receiving events from both of those streams. So it's a new stream derived from those two streams. And this stream will have either the mouse move event or the key press event. So it's not going to return some like unified object. It will be either types of those objects. And usually in these systems, there's usually a wrapper object which contains some timing information or time stepping information because some of the systems we'll talk about have time stepping and some do not. So then the other type of object we have are behaviors or signals as they're referred to in a lot of the early like Connell Elliott literature. So signals are basically going to be values that have values over continuous time. So the example of mouse position, depending, because there are obviously edge cases there, but let's say like mouse position on the monitor as a whole, or the screen as a whole, the entire viewport of your computer, that mouse position is always going to have a value, and that value is going to change at discrete points in time, but it always has a value, so value over continuous time. Also, an input field, which we'll talk about here. Imagine that we have an input field on an HTML page. That has a value over all time. Then we run an operation, which is a lift, which is basically applying a function to it. Some of this nomenclature comes from Haskell, so I'm just going to gloss over it quickly. But so I2 would basically be a function applied to I. So let's say that I was the text field. The function that's used to perform the transformation is going to be a map that converts that value to all uppercase, or maybe a color, depending on some function that takes values to colors based on the length of the string or something. And then I2 represents another behavior which has a value over continuous time, and that would be the transformation applied to it. And these behaviors underlying have event streams. So the behavior is just cache, essentially, if you think of it, it's just caching the last value of its saw of a event stream that's going to encapsulate. So that event stream, will have the change events, that's going to have a value. Every time that value changes, it's just going to kind of store the state of that value. So a lot of these, we'll see the differences in a lot of the FRP frameworks when we get there, but they have this changes operator, which is going to kind of take the event stream that's inside of this object and expose it again so you can treat it as an event stream again. And then, like we just talked about, we can call operations like map, filter, all sorts of things like that. And then you can have a derived value based on two behaviors. So if either of these two things change, we'll apply a function and return a new one. So it's very similar to the merge, except it's going to store its last state. So then FRP systems usually have this concept of switching. So event streams, you can have higher order event streams. We can have event streams that produce other event streams, and we can basically change the behavior of the system based on that higher level composition of event streams. So here we have key presses of the A button, key presses of the B button, and let's say that we have something called key presses. These are all event streams. So what we can say is, we can build something to say, well, return whichever of the latest of these streams was most active, return the latest event in that stream. So we can get a series of A key presses, and then if the B key starts getting pressed, we can convert and start returning those B streams. So it's like higher order event streams where we can be returning events of either type. So this allows us to completely change the operation of the system based on events that are happening. And we'll see an example of that shortly. So then there's this idea of glitch-free propagation. And not all systems have this, but in some systems, this is a desirable property to have. So if you imagine we have, see how you messed this up on this next slide again, so we'll just look at this one. Imagine that we have A, and A is being derived by B and C. And then we had something like this, where we had these values being derived like this. This graph is wrong, so just bear with me, because I have a better one coming up in a minute. We need to ensure that we do a topological evaluation on this graph, so that we evaluate basically like a breadth-first evaluation. So we make sure that we evaluate all the dependencies of those objects before we evaluate their dependence. So if we kind of look at this example, this shows what's classically called, I guess, as like a violation of a data flow invariant. We have these series of commands we've run over here. We have A equal to Y plus 0, B is equal to Y plus A, C is equal to B plus 1, D is equal to C modulo 2, and then E is equal to 5 divided by D. And so this represents our dependency graph here. If we were to traverse this graph by doing a depth-first evaluation on Y, and B happened to be evaluated first, we basically, by order of doing all of those computations, get a divide by 0 when we go to evaluate E. So what we need to do is ensure that before we recompute B, we've already computed all of its dependence. So some systems do have this, some systems do not have this. It's up to the application concerns if you need this. Obviously, this slows down propagation in the system because doing a topological sort on the graph can sometimes be expensive unless you implement optimizations for it. And then in most of these frameworks, we'll kind of just take a glance at what the common operations we have here. We usually have things like the ability to merge event streams. Every time we get an event, just to emit a constant value. Convert things back and forth between event streams and behaviors. There's map to do a transformation, delay to delay the propagation of a value through the graph, collect, which is kind of like a reduce, filter once, filter repeats, which allows us to repeat values as if they get emitted over and over and over. We can basically say only emit one of those to the next stream. Snapshot values, which snapshot event streams, which return things back to values, and the ability to kind of skip values in the stream. So there are a bunch of implementations. There are a lot of abandoned implementations. We'll kind of talk about 3 of the big ones that everybody kind of knows. So Flapjacks is the big one. This is one of the first ones implemented in JavaScript to handle a lot of the concerns that were in many of the Haskell implementations, if you're familiar with any of those. So it provides a language and a framework. It's got a Haskell compiler. It can emit JavaScript code, or it provides a JavaScript runtime that you can put right in your program and interop with the rest of the JavaScript in your program. There's a cool paper about it if you're interested, OOPSLA 2009. It was written by a couple people that I know, and it's one of the first like really major implementations of JavaScript that covers a lot of the issues that we've seen in them. So we'll kind of briefly just look at the code. So here we're defining a timer behavior. So timer B is to get a timer, so a timer that's going to emit a value every 100 milliseconds, and that value is going to be stored in a variable that we always can get whatever the current time was. So if you kind of want to think about that as an event stream, it's going to be an event stream that's going to tick something every 100 milliseconds, and then it's going to always provide whatever the last tick was if you try getting its value. And then we can just call math.floor and 10th b divided by 1,000. There's an interesting thing to note when looking at this code. We're taking that behavior, which is going to have a value that's going to vary over time, and divide it by 1,000. So how does that actually work? So this is actually calling it's actually exposing the event stream and calling and setting this to be the function of evaluation every time that event stream emits a new value, and then saving that value. So this in functional reactive programming is going to be called something called transparent reactivity, where you actually don't have to use special operators to do this kind of mapping. Here is an example where we have a timer that we're going to treat as an event stream, and every so often when that emits an event, we're going to call map function, which is going to return window.location.hash. And then building upon what we just did, we'll define something called route which will basically take that hash every time it changes and call another map function to return either this sliced value or a default route, whatever that happens to be set as. And this example is actually in the to-do FRP GitHub repo, which has a bunch of FRP examples of various to-do applications, which is like the hello world of FRP, so to speak. And then here what we can do is convert the route to a behavior from an event stream by calling this starts with. So we say we'll start with the default route. We're going to filter repeats on that route event, so we only want discrete changes of that. We only want the unique changes on that event stream, which has discrete changes. And then starts with converts it to a behavior. So route B is a variable that you can get its value at any time, and that will represent this transformation of all these operations we had before applied to the window location. To provide a little bit more complicated example, this is the idea of switching, where you want to change how the system is going to operate over time. We're going to have a start event, which is basically going to extract events of something being clicked, and we're going to map it to something which is going to return event streams of the value of a particular edit box. And then we have this other event stream called stop edit, which is a merge operation applied to return being pressed in that edit, so a stream of return being pressed, and a stream of blur events happening on that event stream as well. And we're going to map that to an event stream that's going to return just one value, which is a sentinel value. And then we build this event stream by calling switch, and that's going to fire the innermost values of the merge of these two event streams. So when somebody double clicks on that label to edit it, it's going to start firing events that represent the value in the box that they're editing. And then as soon as they blur or happen to press the return button, that stop stream is going to be switched to, which emits just the sentinel value, and then the editing stops happening. So it allows us to say, given a certain set of conditions that happened on one particular event stream, stop observing that and start listening to events that happen on this other event stream. So that's how we can change the behavior of the system. So that's Flapjacks. There's RxJS. This is kind of come from the Microsoft world. This is authored by the Cloud Programmability group at Microsoft, Eric Meyer's group. It's a set of libraries that provides reactivity. A lot of this comes from .NET. There's a JavaScript version. There are bindings in various languages that are going to provide this reactive changes to do this kind of work with those. It has the ability to change kind of how the scheduling and time stepping is done of values being propagated through that dependency tree. And it's kind of made up of these two main interfaces called observables and observers. So you have observers, which are going to listen to events on event streams and perform operations on them, and then observables, which are going to kind of be these lazy arrays that have values that can be subscribed to. And RxJS does not have the glitch-free propagation that we talked about earlier. So in this example, we're going to just take an input field and monitor for the key up event. Every time we get that event, we're going to call this select, which is going to get the event and abstract the value. And then we're going to emit values only when the value of that is greater than 2. And then we can basically compose that as well. So now we can throttle that to every 500 milliseconds. So no matter how many values we get during a 500 millisecond period, we're always going to fire the last one. And then we can build another off of that by composing it and call this distinct until changed method, which will not change that value until we get the new value. So even if you get the same ones, it's not going to continue propagating those. And then to show off how we can kind of switch the system here. So in that input field, as people are typing, we're going to select the values as we get them and call this search Wikipedia function, which is basically going to launch AJAX requests to Wikipedia for a particular term. And then switch latest is, so let's say the user does a lot of operations and those AJAX calls are taking a really long time because they're on like a 2400 baud modem or something. What switch latest is going to do is say, don't listen to any, if I get another event, don't listen to any other events because I'm waiting for the latest one. So it allows us to always be observing for that last change that's going to come through the event stream. And then we can just kind of perform a filter here on the results as they're coming out. And here, if you look at the bottom, when we have the subscribe, this is showing off the observer. We're going to have the subscribe function, which is going to listen to results that are coming out of that stream, and then we can do something like insert them into the DOM or whatever type of operation we like to do. So another one that I actually am not super familiar with, but I did a little bit of research before this talk, is Bacon.js. This comes from Flowdoc. I guess Flowdoc is the company name and the product name, maybe. It was open sourced in 2013, so I think in January of this year, or that's when the first blog post was. This is inspired by RxJS and Reactive Banana, which is one of the really, really early Haskell implementations of this kind of like programming model. And Bacon.js, as far as I can tell, does not have the glitch-free propagation that we talked about earlier to ensure that we don't have those data flow invariants violated. So here, Bacon has an adapter for jQuery, as RxJS does as well. We have a click stream, so we're getting this object on H1, and we're converting all of the click events into a click stream. And then every time we get a value on that stream, we're just going to call the alert function. And all of these examples are taken from the docs, so you actually can go play with the code and get a feel for how this works. And then here we're showing how we can take this event stream. So we have clicks on a plus object, clicks on a minus object in the DOM, and we're going to map the plus objects to the one value. So we'll get a stream of one value, a stream of ones every time that value is clicked. And then for minus, we're going to get a stream of negative ones for every time that the minus is clicked. And then both is going to be the merged event stream. So we're merging the minus stream into plus. So that's going to return a new event stream that's going to contain either of those events. So you can kind of see all of these things have a lot of different syntax, but we're kind of performing the same types of operations. We have these streams. We're going to perform aggregation on these streams or mapping or some sort of transformation, and then we're going to change the behavior based on how these streams work. So here we define a function, add, which takes x, y, and returns them being added. And then we call bulk.scan, which takes an initial value and will perform a function, which add we're passing to it, over that entire event stream, and that will be reactive, so those values change. And then every single time counter changes on the value, we'll basically just update the DOM with the sum. If you want to have something derived from two different properties in the system, which is Bacon's word for a behavior, we're defining a function that's going to take A and B. It's going to log the addition of those two numbers. And then we basically call Bacon.onValues with two event streams and the function to be applied. So this is going to, Bacon.constant1 is going to return a constant stream of ones. Bacon.constant2 is going to return a constant stream of twos. And then we say whenever those change, we'll just basically run this function f. So that's how you do. So in the Flapjacks example, if you remember, we just had two things. We just did the add operation. Dude, what? Computers. Okay, so you remember in the Flapjacks example, we were just able to take two of those behaviors and do the add operation between them, and it automatically knows that when either of those two changes, I have to do it, the transparent reactivity we talked about. Here we have to do something a little bit more explicit where we say, well, on either values in either of those streams, we have to redo that computation. Similarly, on that concept of switching that we talked about to change the behavior of the system, here we basically are taking mouse move events and key down events and returning an event stream of those. And then we're calling flat map latest. So what that's going to do is, so this one's a little bit more complicated, but that is going to take out of these two streams, bacon.one's true, so a stream that's going to return one value of true, and then a stream that's going to return one value of false 30 seconds later. So if activity keeps happening, that activity stream will keep firing events. And if that keeps firing events, it will keep firing that once.true event for active. So active will always be true. And it starts with true, with the toProperty true. But as soon as there's no activity for 30 seconds, we're not getting events in that activity stream anymore. So that false function will fire, and then active will immediately become false. So this is how you can change the behavior of the system. And obviously, in this return value here, you could do some sort of more complicated examples, as we saw in some of the earlier examples. So how could you apply this to Node.js? So RxJS has an npm module. This is going to get you all of the normal JavaScript reactivity stuff that you would get from its JavaScript implementation. But this is also going to provide some reified interfaces. So it's going to create asynchronous objects for receiving events. It's going to basically provide its own reified implementations of node, child process, DNS, events, file system, HTTP, HTTPS, and all of these. So to see how that kind of works, we see this is taken from the reification of the HTTP method. So HTTP get is going to be changed to basically have this asynchronous subject. And it's going to say that if you see down here on line 10, there's a handler that's passed, and that handler is basically getting a value, inserting it into that event stream, immediately called completing on it, and then error also has its error handler, which is going to end that stream with an error. So every time you call get, you're basically going to get like a higher order stream composed of a series of streams representing each of these. So there's one of these for get. There's one of these for create server as well, where you're going to get an event stream of the subscriptions as they come in, which will be the request coming into the server, and you also have a request as well, so HTTP request. With Flapjacks and Bacon, for example, Bacon has a Node module. I've never used it, so your mileage may vary, obviously, as meme-ish as that is. With Flapjacks, you can use it with Node. There have been some successful uses with Node on the mailing list. There gets into some problems with how to handle certain types of returns. I don't know all of the details about that, but Flapjacks allows you to create event streams and inject values into those event streams manually. So you could create an event stream and then create some sort of event listener that's basically going to just insert events into that stream and then build the rest of your application on top of that. There may be better ways to do some of the create server operations and things like that. There are some other options if you're interested into them. ClojureScript, obviously. ClojureScript is an area where functional reactive programming, so ClojureScript, for you that are not familiar, is a subset of Clojure that compiles to JavaScript using the Google Clojure compiler. There's a lot of interest in functional reactive programming there, obviously, being a Lisp. There's two libraries that are in active development. Shafty is one that I wrote, which is an implementation of Flapjacks, the Flapjacks core API, so to be able to create event streams and change behaviors and do all sorts of stuff like that, not including the DOM API, so that's authored in ClojureScript. And there's also one Javelin, which was written by a friend of mine, Alan. This is a little bit different. Javelin is a simplified model. They get around some of the problems with glitch-free propagation by doing kind of more of a spreadsheet model where you can build a bunch of dependent cells on one cell, but you always need to kind of go back to the original cell to make changes to have them propagate through the graph. So these are really two cool libraries if you're interested in that. Shafty does work with Node.js because I did test that a long time ago when I was implementing it. You can obviously do all of the ClojureScript stuff with Node.js as well. And there's also Elm. Has anybody here heard of Elm? Yeah, cool. So Elm was written by Evan, I can't remember his last name right now, at Harvard for his PhD thesis. So Elm is a language that has a compiler written in Haskell. I think most of it's authored in Haskell that will emit CSS, JavaScript, and HTML for doing this. So it's a way of basically building these functional reactive programmings using this custom language that he put together. And that's my overview.